All right, so this video is going to look in detail at the addition of nucleophiles to acid chlorides. Again, we can make an acid chloride from a carboxylic acid by reacting the acid chloride, or sorry, by reacting the acid with SOCl2. We can't go directly, right? There's no way to do this. For one thing, hydroxide is a bad leaving group. It can leave. We're going to see examples later in the semester where it does. But the other problem is the nucleophile is going to be a base, and it's just going to take that proton. All right, so you can't just add nucleophiles under basic conditions. So I guess I should say under basic conditions. We can't just add nucleophiles straight to the carbonyl. So you have to turn it into something else. Well, not the easiest. This is actually probably not the most optimal way to do it in the lab. On paper, the easiest way to do this is to make the acid chloride. Acid chlorides are really unstable. They're very sensitive to water. It's summer in North Carolina. There's a ton of water in the air. And so these start hydrolyzing as soon as you make them, basically. All right, but if you can make them, then you can treat them with a nucleophile and get a whole variety of carboxylic acid derivatives. So let's look at, I'm not going to talk about this one. I'm not going to talk about the thioester. The thioester works just like the ester. So let's do a specific example. Let's look at turning benzoic acid into this ester. Okay, so what we need to do, like I said, reflux benzoic acid and thionyl chloride. This gets us our acid chloride, and then we can treat the acid chloride with the alcohol, and we put some base in there. All right, and so there's going to be an equilibrium here between. This equilibrium really favors the starting material, but we'll have a little bit of this alkoxide, and then that alkoxide can add in. And now, an important thing, you can't do a direct SN2 on this carbon. All right? The direct SN2 would have to come directly from behind here, do an inversion, and this is protected by substituents, and this molecule is planar, so the nucleophile has no route to directly access the sigma anti-bonding orbital of the carbon-chlorine bond. Okay, so this has to be an additional elimination step. So we'll get this intermediate. So addition. And then the O- can now kick the chloride out, right? Chloride minus is a much better leaving group than O-, and that gets us our product. Okay, you can do this. I should say here, that triethylamine can be any base that's strong enough to pull this H off, at least a little bit. You can use a super strong base and just make the oxygen anion, that's fine. Or you can use kind of a mild base like triethylamine and establish an equilibrium where there's just a little bit of this O- in there, but then once it's there, it reacts, and that drives the equilibrium between the base and the alcohol. All right, so I'm going to erase this. You can pause and watch it again if you want. I'm just going to go back. You didn't mean to remove that. So we get our acid chloride. You don't need to know the mechanism. I'm not going to ask you the mechanism of the thionyl chloride reaction. Acid chloride, and basically to get an ester, you're going to have an alkoxide that adds into the carbonyl. All right, there's your tetrahedral intermediate. So we go from a trigonal planar atom to a tetrahedral atom, and then this O- will swing some electrons down, kick out the chloride, and we go back to a trigonal planar molecule. Okay? You could do this with Rs-, and then it's going to work out. All right, again, go ahead and hit pause if you want. I'm going to show it with the amine. Amines are a little trickier. So let's say we want to go to the diethylamide. Okay? Once you get your acid chloride, then you need diethylamine, and you can either use two equivalents or one equivalent of triethylamine and one equivalent of amine. And now, you don't deprotonate the nitrogen first. All right, the NH has, this neutral NH has a pKa of like 33. Triethylamine is not a strong enough base to pull that proton on. So what happens is the nitrogen adds in. Methyl H plus chloride. And now this looks weird. All right, I don't like the way the book does this. Now you're going to need a base. And so the base can either be a second equivalent of dimethylamine, whatever amine is your nucleophile, that can be the base, or we usually use triethylamine. Triethylamine's cheap. It's not nucleophilic because the ethyls are too big and it doesn't have a proton to lose. And so with dimethylamine, honestly, I might use just two equivalents because it's cheap as well. But say you're adding some amine that you spent 6 months making, you don't want to use two equivalents of that, right? You want to use as little of it as possible. So we're going to have some base. It can be any base. And then this base is going to take this proton. It's essentially an E2 elimination. This looks weird, I know. You're taking this proton, you're leaving an O minus. Let me show you what this gives. So you remove that proton from the nitrogen, and you get this compound that's got a carbon-nitrogen double bond with a nitrogen plus, and a CO single bond with an O minus. So what's the relationship between this molecule and that molecule? You can hit pause and think about it if you want. All right, they're resonance structures. Okay, so you typically aren't going to have. The book has the O minus swing down, kick out the chloride. You end up with a plus here. You don't want a plus next to a carboxylic acid, right? So let me get the red pen. That looks fine, right? Why not do that? Well, this carbon is really strongly partial positive. The nitrogen sitting next to it's positive. Like, you don't want those positive atoms together. You just remove this H and kick the chloride out at the same time, and you go straight to the amide. You don't have that really unstable intermediate.